All right, good morning, everyone. Thank you very much for the organizing committee for inviting me here and to be with you and share some thoughts on the distant universe. As I said, my name is Leindert Boogard. I'm a postdoc at the Max Planck Institute for Astronomy in Heidelberg, Germany. And so let's see if I can figure this out here. Yes. So the distant universe, we're going to cover this in two sessions this week. So on Friday, we're going to go out into Cosmic Dawn, where Leah Morabito will talk to you about a number of topics we have put under this umbrella, including H1 21 centimeter intensity mapping, also AGN-related topics, and cosmology. Today, I was going to focus on what we dubbed cosmic history, so galaxy evolution and star formation across cosmic time. Now, if you think about galaxy evolution, we've come a very long way in our theoretical understanding, and I thought perhaps the easiest way to summarize this is to show you this quick movie from a cosmological hydrodynamical simulation. This is illustrious TNG. And if you look here in the bottom left corner, you can see a picture of the dark matter density of the universe, which dominates the overall gravity. Now, in the central panel, you see the gas density. And if I start playing this, you see how we think galaxy evolution works. Gas accretes from very large scales from the cosmic web onto dark matter halos, where it can cool, collapse, form stars, and in this way fuel star and black hole formation. Now the stars and the black hole themselves then put back energy into the gas, potentially driving winds and outflows, and in this way start up a cycle of gas accretion, inflow and outflow, and star formation, which is central to our understanding of galaxy evolution. But what's very clear is that this involves many processes over a vast range of scales, all the way from the large scales of the cosmic web down to the very small scales inside the molecular clouds where the star formation actually takes place. So, and while we have a very well-developed theoretical understanding, there are actually still a lot of unanswered questions and constraints that are missing in order to advance, to see whether what we think is right is actually right. And these questions relate to how the gas supply in and out of galaxies actually evolves and how the accretion processes evolve in detail and how these evolving galaxy properties actually impact the star formation and galaxy growth. So now let's move to the observational constraints that we actually have. And I'm showing you here a very well-known plot. This is the cosmic star formation rate density, and maybe a slightly different representation that you know it. But we've known for some time now that the star formation rate density in the universe increases from high redshift to a peak at around cosmic noon between redshift 1 to 3, and then declines by almost an order of magnitude to the present day. Now, if you integrate this curve, you get the total stellar mass buildup, and this is what is shown here on this top right panel. In fact, the integral is actually the dotted yellow line that you see on this panel, which is above the observed stellar mass density, which we actually characterize and know quite well from optical near-infrared surveys. And this is because stars, of course, don't live forever, but return a fraction of their mass back into the ISM, both through winds and supernovae explosions at the end of their lifetime. Now, moving to the gas phase. So I think it's now been known for about a decade or so that the atomic gas, so the H1, does not evolve as dramatically as the star formation rate density, with a decline with maybe a factor 2 or so from high redshift to the present. And now finally, moving towards the H2. And the H2 is actually the key ingredient because the H2 is what actually directly fuels the star formation. And in recent years, through a number of very large surveys on the largest interferometers, we have finally added this cosmic molecular gas density to the picture, where we actually see an evolution that is much more similar to the star formation rate density, implying that, to first order, it is indeed the cold gas that fuels the star formation. Yes. But now, if you look at this picture, this looks great, but what we should keep in mind is that this is vastly averaged over space and time. This is really a very zoomed out picture. And while we have reasons to believe that this is, to first order correct, there is a lot of details here that we don't understand. And in fact, especially in the bottom two panels, the number of individual galaxies that are contributing to these measurements is actually not so great. It's actually rather small. And this is exactly the domain of the NGVLA and the SKA, and why we're extremely excited for these facilities, because it is on these three panels that you see here where we expect really a tremendous impact in moving forward in our understanding of these topics. So for the remainder of this talk, I would like to go through these three topics and sort of highlight various science cases that the NGVLA and SKA will be able to address here. And of course, following this talk in a number of excellent talks, we will have these outlined in much more detail, but I'll try to give more of a zoomed out perspective here. So starting with the star formation, so we know the SFRD quite well, and especially now with JWST, we're really pushing measurements out to the very highest redshifts. But I think one major uncertainty that remains in our characterization of star formation across cosmic time is really the unobscured star formation. The obscured star formation that is much more difficult to constrain. And this is exactly where radio continuum surveys play an important role, because the radio continuum, of course, is a dust insensitive tracer of the star formation. And now, in the bright end of the radio continuum, the numbers are really dominated by AGN. But if we go to the faint end of the radio luminosity, we know now, and this is just an example from one of the deep VLA surveys, that star formation greatly outshines AGN activity. And it's really at the faint end of the continuum spectrum where we can start probing these star formation processes very well with the NGVLA and the SKA, and really start tracing cosmic star formation out into the EOR and investigate how these radio continuum calibrations evolve over cosmic time. Now, this is all I will say about this topic, because actually right after this talk we'll have a review, or I have another talk about this by Alison, and also on Friday from Eric. So this is all I will say about the star formation, but maybe just one more thought here on the resolve perspective. These are some simulations that were done last year showing what we might see in terms of resolving the radio continuum with the SKA. So as part of the now envisioned deepest SKA midband 2 reference surveys, they will actually have sufficient resolution and sensitivity to probably resolve the star-forming ISM in galaxies out to a redshift of 1 or so in the radio continuum. Now, separating the thermal and non-thermal components here would also require adding band 1 to these kind of surveys, which is currently not planned. All right. So moving away from the star formation now to the molecular gas. So as I said, the cold gas is really a key ingredient because it is what most directly fuels the star formation. And if we think about the molecular gas, which is made of H2, it is actually in fact very difficult to observe, because the quadrupole transitions of H2 have very high temperature and are typically not excited in the cold phase of the ISM, which means we need to use tracers. And the most well-known tracer is the most abundant molecule, which is CO, and especially the ground state of CO is the best calibrated tracer of the molecular gas. And if you now look at this plot, which is the frequency on the y-axis plotted versus redshift, in gray here I highlight the NGVLA, which will have complete frequency coverage all the way from about 1.2 to 116 gigahertz, with the exception of the water absorption band. And the blue lines here highlight the CO transitions. And what is immediately clear from this plot is that with the NGVLA, we'll be able to trace molecular gas through CO at all redshifts, and especially with CO 1 to 0, all the way from redshift 0 out to the highest redshifts. And the 1 to 0 is especially important because it is what traces, especially also the gas which has very low excitation and low surface brightness, which can which actually has a quite significant fraction of the total mass. And just as an example of this here, I have a nice figure from Emmons et al. Showing how in the spiderweb galaxy at redshift 2.2, you can see that the C1 traces mainly the more compact cold gas, but it's really the CO1 to 0 that is reservoir that is much more extended. Now, with the NGVLA core and the shortest, baselines at about 1 kilometer, we'll have perfect sensitivity to resolve these kinds of gas reservoirs of cold gas out to CGM scales at these kinds of redshifts, which is very exciting. So how does the SKA fit into this picture? Very briefly, with band 5, as planned, goes up to about 15.4 gigahertz. And this means it will be able to observe CO at very high redshift, so CO1 to 0 above redshift 7 or so. But really to trace cold gas across cosmic time with the SK would actually require to push it out to a bit higher frequencies. All right, so if we now look at the molecular gas budget again, this is another version of the plot from some summary work we did last year, highlighting now the various observations we have from ALMA, NOEMA, and the NGVLA in constraining the cosmolecular gas density through these kind of spectral scan surveys. And Just to help you appreciate these, what look like rather big boxes, these are really hundreds of hours of measurements on the largest interferometers. So with ALMA, the ALMA Large Spectrum Aspects, COLD-Z on the VLA, the NOEMA Hubble Deep Field North Survey, and really provide an unprecedented view on this. But it's also very clear that with current facilities, it's going to be very difficult to improve on this unless we really start making extremely significant investments of over thousands of hours, which is unlikely to happen. Now with the NGVLA, which will have an order of magnitude improvement in sensitivity, this will really be the way to leap forward here. So both the large bandwidth, increased sensitivity, but also the large field of view at lower frequencies will really boost the survey speed here by a factor of 25 or so and enable us to characterize this curve in much more detail and measure how the global gas budget in galaxies evolves, as well as the gas consumption and accretion timescales. And then you might say, well, this is great, but I could have drawn this purple curve, go through these boxes, right? Do we really need to build the NGVLA to do this? And the answer is yes, because at each of these boxes, there's only a few galaxies contributing. But the number statistics that the NGVLA will bring will actually enable us to, at each of these redshifts, break down the H2 mass function and couple it to the stellar mass function and really start characterizing, how the physical properties and the gas properties of galaxies relate at each of these redshifts in detail. And this is really the type of constraints that we need also to connect to the theory and constrain the models of galaxy evolution. To zoom in on this in a little bit more detail, just a slightly different representation of this. What this plot shows you is the gas fraction of galaxies as we go to high redshift. And we've known for some time now that galaxies at high redshift are significantly more gas rich. A massive galaxy at or beyond a redshift of 2 actually has more molecular gas than it has stars. And we know this must impact the physical properties of the galaxies. But how exactly this impact takes place is really not known because we're just lacking statistics. And the NGVLA will exactly provide these statistics because of the much larger samples it gives. And this will enable us to do studies like this. So this is work from the cold gas survey at redshift 0, where they've measured CO1 to 0 molecular gas masses for a very large number of galaxies all across this stellar mass star formation rate plane. And you can see how the gas fractions actually change in galaxies with higher and lower star formation rates. But doing this at redshift 2 is currently, very difficult. And the NGVLA will actually allow us to do this and see, do the picture we have at redshift 0 actually matches, the picture that we have at redshift 2. And this is not limited to redshift 2, and we will actually be able to push this out to much higher, further distances. And just as an example, this is a JVLA CO2-1 detection in a redshift 6, very massive, but still sort of main sequence star-forming galaxy. And this currently takes about over 24 hours on the JVLA under the best weather conditions. Now, to reach the same sensitivity, and I did the math just before this talk with the latest NGVLA numbers, takes about 26 minutes or so with the NGVLA. And that means that we can really start now we can start when the NGVLA is there, really start collecting these kinds of measurements for a large number of galaxies and characterize what I just told you all the way out to redshift 6. And at that sensitivity, there's actually also room to follow this up at high resolution observations. So moving now away from the integrated measurements into the resolved measurements, here are some simulations that show you what a 20-hour observation of the model, which is shown here on the left, with both the ALMA on the far right and the NGVLA will give you. And this is some work that's been done by Chris Riley and Masha Neleman some time ago. And what you can see is that with ALMA currently, there is, in theory, sensitivity, and the baselines are long enough to do these kinds of studies and characterize the resolved, molecular gas at redshift of 2. But the fact you have not seen very many studies here is just because this is very hard. It really takes tens of hours to do this, and that's for a single galaxy. And to make progress here, we really need this increased sensitivity that NGVLA will bring. So in the same time, the NGVLA will do a complete map here and resolve this galaxy, at subcolor parsec resolution, meaning that we will be able to trace the rotation curve and measure the dark matter and baryon fractions at various radii, but also model the gas substructure and see how the gas actually precipitates the star formation. And finally, also, this will help to measure also the dynamical structure, and particularly also the dispersion and potential gas outflows, which constrain the energetics inside the galaxy. And this is extremely important to connect back both to theory, but will also really help to connect back to all the multi-wavelength observations we're now gathering, for example, with JWST, which actually has the same resolution and can resolve these kinds of galaxies in their ionized gas and in their dust extinction. And we will be able to connect these two then finally with the NGVLA for large numbers of galaxies. Right, moving away from CO, it's not the only molecule in the cold molecular gas, but there's many other tracers, both the optically thin CO isotopologues, dense gas tracers, water, and of course even more complex molecules. And these trace various phases of the gas and various processes, but are really an order of magnitude fainter. And it's exactly this order of magnitude that means that, the way to think about this, at least the way I think about this, is that what we can do with CO now, with the ALMA, is what we will do in dense gas with the NGVLA, basically. Which means that if you do a single pointing on a galaxy, and I'm showing you here, just a subset of dense gas tracers as they move through the NGVLA frequency windows, you'll get a lot of lines in a single NGVLA exposure, and really start, which will really enable us to start characterizing the gas phase and the physical conditions in the ISM of typical galaxies at cosmic noon in much more detail, which I think is extremely exciting and also very important in order to understand the physics here. And now finally, to push really out into the redshift frontier and the first few 100 million years, I think we're all very excited with JWST, and we're seeing, galaxies now being confirmed beyond the redshift of 10. Here in the bottom left is just one of these examples. This is the most famous high redshift galaxy before JWST, I guess GNZ 11, which indeed has been confirmed to be a beautiful high redshift galaxy at redshift 10.6 with a strong Lyman break. And there are actually spectroscopic confirmations, beyond this, with I think the current record holder being redshift 13.2, but there are photometric redshift candidates going out to about redshift of 16 or so. Now, with the NGVLA, if these massive galaxies exist beyond the redshift of 15, it will have actually the capabilities to detect them in C++. And this is again some simulation work done by Chris Carilli, which you can see here on the right, where I'm highlighting the sensitivity of the ALMA and the NGVLA. And for the metallicities and star formation properties that these galaxies are now sort of constrained to have, the NGVLA will actually have sufficient sensitivity to detect them. So if these kinds of galaxies are out there beyond redshift 15, we'll get them with the NGVLA. Good. All right. So concluding now on the more cold gas and moving finally to the atomic gas. Okay, so the atomic gas plays an important role as well, and the H1, because the H1 is actually what gas accretes from the cosmic web into the halos in the form, and then cools, into the H1 reservoir. It's H1 is the mass budget from which the H2 that fuels the star formation actually forms. Also, in the local universe, the H1 is extended on much larger scales than the H2, as many of you know, and this actually means that it's a much better tracer of the dark potential and the dark matter out to large radii. Now, if we look at this H1 plot that I showed you in the beginning in a bit more detail, one thing to appreciate is that this is actually a very difficult measurement to make because the H1 emission is very faint. And in fact, there's only very few direct H1 detections beyond the redshift of 0.1 or so, with the previous record holder was around redshift 0.4, and as of a few months ago, we have a lens detection at redshift 1.3. But really, beyond the redshift of 1, most of these constraints actually come from H1 and absorption, and that means that this evolution that we're tracing here, I think, is still there's still significant uncertainties here that need to be addressed. Now, where does this lie in terms of the SKA and its pathfinder? So again, looking at this plot, the SKA mid will cover H1 all the way from redshift 0 out to, in theory, about a redshift of 3 or so. So I think in practice, sensitivity-wise, it will probably be limited to around a redshift of 1. And then at higher redshift, it will move into the SKA low regime, where it will again be characterized, can be characterized through intensity mapping experiments. And I will not talk about this. This is something that Leah will address on Friday. So why do we care about the H1? So why do we care about the H1 in terms of the physics of galaxies, and particularly also inside the galaxies? I think one interesting thing to look at here is some theory that is perhaps slightly older already, but I think still really relevant. This is some work from Daniel Breshko that shows you how the H2 to H1 ratio actually theoretically is predicted to vary in galaxies. So as you go out to high redshift, galaxies get smaller and more gas-rich, and this means that the ISM pressure is higher, and that the theoretical expectations are that the H2 to H1 gas ratio is actually increased. And yeah, I think we can see this on screen, right? This color goes from blue to red to increasing H2 to H1 ratio as we go to high redshift. And that means that this ratio can actually be used as an ISM barometer. Now we can't really measure this, but just as a thought experiment, I just thought let's put the global densities here for a second. So this plot actually divides the bottom two panels I showed you before of the molecular H2 density and the H1 density. And what you see here is indeed that, up to from redshift 0 out to redshift 1, we indeed see an increase, but actually after that it doesn't increase anymore, it just sort of goes down. Now, when I thought about this first, I thought like, well, actually there's lots of uncertainties beyond redshift 1, so maybe, we're just not really, we're not just quite sure what this curve should look like. But in fact, I think what's really key here is that what we're looking at here is really the global H1 budget. And a lot of the H1 is not in the disk, but it's actually sitting out at larger radii. So in order to really do this, we really need to characterize the H1 also on these smaller scales. And hopefully with upcoming pathfinders, and eventually the SKA, and we will be able to start doing this slowly, pushing out into the higher redshift regime. So in the last minutes, let's look at what's there to be expected. So sort of, this is very broad, but this is sort of the realm of the current H1 detections. But there are several large H1 surveys planned through the 2030s on various SKA precursor and pathfinder telescopes. Both on MeerKAT, ASCAP, ongoing programs on the VLA. And this is not an exhaustive list for sure. And this will, especially with surveys like LaDuma and the UHF band, potentially push us out to a redshift of 1 or so. Now with SKA mid, this will be really a huge step up in sensitivity in some sense, and we'll really have an opportunity to extend and follow up on these pathfinder surveys here, out to about redshift 1 or so. One thing that I think is very important is the synergy with multi-wavelength, large area spectroscopic surveys that are coming online to really push this also through stacking. And then finally, on the much longer timescale, I think, the dream is eventually to push this out into much higher redshifts with, a very much larger increase with the SKA2. And I think it's really something also to keep, on the horizon. Good. All right. So to conclude, I hope that taking you through this sort of zoom out picture got you all excited for how the NGVLA and the SKA will really have a tremendous impact on characterizing both the star formation and gas processing galaxy out of high redshift. And I hope that in the upcoming talks, we'll really see many more of these science cases highlighted in more detail. And I think there's really a lot to learn. So, the future is looking bright. Thank you.
We have plenty of time for questions. So are there any questions from the audience? Carla?
Okay, you can hear me. Thanks for a great talk. So do we expect that, and excuse me, this isn't my basis. Okay. Do we expect that there would be a time when the star formation would overtake the amount of gas in galaxies? Do we have examples of where there is more stars than gas at a particular?
You mean in the sense that the galaxies run out of their gas, basically, or
yeah, or that there are more stars than gas? Yeah.
Yeah. So I think, in the local universe, there's many examples of galaxies which have the bulk of the mass is in the stars and not in the gas phase, and it's really. Now that we go out to higher redshift, we start seeing these galaxies which are really dominated by their cold gas phase and have actually much more gas than stars. So I think that's really the fundamental difference that we're trying to understand here between the local and the high redshift universe. Yeah.
Okay. Thank you.
Hi, can you hear me? Oh, okay,
can.
great presentation. I'm wondering about the H2 to H1 ratio, whether perhaps the photodissociating UV flux plays as much a role, perhaps, as the ISM pressure for determining that.
Right, that's a good question. So I think the answer is yes, but I don't think I can give a much more detailed answer here. I mean, what we know is that in these, as you go to high redshift, with the much increased star formation, of course, the UV field in these galaxies will be much more enhanced, right? So there will actually be a much stronger radiation field, and besides the ISM pressure. So I definitely think this plays an important role, and will be important to take into account. But how exactly that impacts this picture, I will not be able to tell you from the top of my head. But
So we've got a question over here from Christina. Oh, no, Peter. Okay.
Well, just following on the photodissociation
Yes.
question in the early universe, which I used to work on that, reaching into my past, I must admit. But the actual formation of molecular hydrogen from atomic hydrogen is a fairly complex process. It just doesn't happen like that. And with that very enhanced radiation field, you might expect to find an equilibrium between dissociation and association, or formation, if you like to call it that. And it, would have been interesting on your initial slide to see an arrow going from H1 to H2 to try to figure out exactly when that might have happened and how it evolved.
Yeah. Yeah, I agree. Yeah, thanks.
Christina.
Hello. Okay, that was a really fantastic talk. Thank you so much. I think you made it clear that the strength of the NGVLA will really be for looking at the molecular gas, history of the universe. But what are your thoughts on the NGVLA's role in H1 science, since it will, I think currently it goes down to 1.2 gigahertz and would cover H1 at low Z.
Yeah, so I mean, I'm really focusing on the distant universe here, right? Which is why I didn't talk about, H1 locally. I think there, of course, there's really high anticipation of the NGVLA. But of course, in order to push this to higher redshift, we'd really need to add the lower frequency capabilities on the NGVLA. I mean, so I think the current plan is 1.2 gigahertz, which only gets you to a very low redshift, right? So but locally, yes, there I think it will have a major impact for sure. Yeah, I'm not sure if this answers your question, but yeah, no, that would be. I mean, and if there were opportunities to, extend the NGVLA also to lower frequencies to do this at a high redshift, I think that would be extremely exciting. Yeah.
A lot of the baryonic mass is in ionized gas in the halo and in the CGM. So what are the surveys or the telescopes we're going to use to get that phase out to similar redshifts and similar populations? Right.
So that is a good question. I mean, for the picture that I've painted here, right? I think in terms of the star form process, it's really the cold gas in the halo that we care most about. But you're absolutely right to say that the gas on larger scales is very important. I mean, I think there's various probes, for this, including X-ray missions and things like that to probe this. But it's also a bit out of my field of expertise, so I won't be able to give you a list of detailed probes here. But yes, I agree. Yeah.
Over there, Michael.
Centimeter wave astronomers have always looked with great envy at optical spectra with tons and tons of lines, right? But when we're talking about redshifting emission from the millimeter down to the centimeter and such, you'll get tons and tons of lines. If I were an optical astronomer, I'd be playing games with looking at template spectra, comparing to models and these kind of things to effectively stack up all those lines with the appropriate weighting. So that's never discussed in these kind of talks. Is that something that's just not useful because those lines are so faint and there aren't enough of them to make a big difference? Or do you think that will become interesting as we get these huge bandwidths?
Yeah, no, I mean, I think, I only briefly touched on this when I talked about, other gas tracers, but I think, if I understand your question correctly, I think that is exactly the regime that we will be moving in for more typical galaxies with the NGVLA, right? I mean, if we think about these spectral scan surveys we do for the gas density, right? You scan and you only see CO. If we do this with the NGVLA, we'll get lots of lines because you suddenly get all these fainter lines as well, which are currently really just outside the regime of the observations. So yes, I think then we'll definitely also move into modeling these simultaneously, and this already, I mean, we saw talks on this yesterday, for local galaxies, this is already what we are doing. I think really at Redshift 2, there's just not the sensitivity to get many of the fainter lines for all but the brightest galaxies. But yes, with the NGVLA, we will definitely do this, yes.
I'm afraid we're out of time, so if there are more questions, we can take up in the tea break, but thank you for an excellent talk.
Thank you.